Algebra 1, Lesson 1-3, Real Numbers and the Number Line. Learning targets. I can classify, graph, and compare real numbers. I can find and estimate square roots. Warm-up. If the pattern continues, which will be the first figure to contain more than 200 square units? Explain your reasoning. We'll come back to that. Key concept, square root. So first we want just the symbol. And so we have this object. This object is called a radical. Oh, hey, look. It's a cat in a square. It's really a kitten in a square. Isn't that cute? So the object's called a radical, and we also think of it as a square root. The algebra of a square root, a number a is the square root of a number b if a squared equals b. Another way to think of a square root is the square root is asking the question, what number times itself equals this? And that's what we see here. What number, in this case, a squared, equals the number b? So a would be the square root of the square root of b. As an example, what is the square root of 49? So we can write this symbolically as the square root of 49. It asks the question, what number times itself is 49 is the question. And that, of course, would be 7 times 7, or 7 squared. So that tells us that the square root of 49 equals 7. All right, example 1, simplifying square root expressions. What is the simplified form of each expression? Well, looking at the square root of 64, 64 is under the radical, I know that 8 times 8 equals 64. So lo and behold, the square root of 64 is 8. Similarly, 5 times 5 is 25. So the square root of 25 is, you've got it, 5. All right, moving right along. So a little trickier. Here is a property of square roots. If I take the square root of a fraction, numerator and denominator, I can break this up. And actually, let me, hold on a moment. All right, that's better. So if I have a fraction under a radical, I can actually break that fraction up into a radical over a radical. So that means the square root of 1 over 36, or another way of looking at that is, which is even easier, is 1 over 6 times 1 over 6 equals 1 over 36, because multiplication of fractions is straight across. This will actually be easier than this property. So the square root of 1 over 36 is 1 over 6. And that's the rule. The next case is similar. The square root of 81 over 121. Well, I know that 9 over 11 times 9 over 11 equals 81 over 121. Therefore, the square root of 81 over 121 is 9/11. Forgot the box and the check. And just looking at all of that at once, there we are. What do we do when the radicand is not a perfect square? Well, what's a radicand, you might ask? The radicand is the part inside of the square root. So A equals radicand. Anything underneath a radical. So let's list some perfect squares. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. And so on. So what if we have the square root of a number that's not a perfect square? Say the square root of 7. Notice square root of 7, 7 is not a perfect square. There is no number times itself that equals 7. So we look in between. I notice that 7 falls between 4 and 9. Square root of 4 equals 2. The square root of 9 equals 3. So we would estimate, using both of those, that the square root of 7 would be about halfway, or 3.5. So that is how we estimate. Example 2, estimating a square root. What is the value of the following expressions to the nearest integer? Well, perfect squares, 1 is 25 is a perfect square because, of course, that equals 5 times 5, as we've already seen. Another perfect square would be 36, which is 6 times 6. So we would estimate that the square root of 34 would fall somewhere in between the square root of 25 and the square root of 36. So we could say estimate halfway, or 5.5. So what about the square root of 387? Is it even a perfect square? Well, it so happens that 19 times 19 is 361, and 20 times 20 is 400. So we notice that 387 falls roughly in between. So again, we'll estimate halfway and we'll say 19.5. Now it turns out that in reality, the square root of 34 actually equals approximately 5.8. And the square root of 387 is approximately 19.7. But those are pretty close without using technology. So we have some ideas from sets. So the key idea here is set. Set is just a collection of things. And we use the curly braces to indicate something is in a set. So it's just a collection. If something is in a set, for instance, if I have the set, which usually would just be numbers 1, 2, 3, 2 is an element of the set. So a subset is just a set that every element of that set is also in another set. So for instance, the set subset let me make that a little bigger. Subset has all of its elements in another bigger or equal set. For example, if one set is 1, 2, 3, a subset for instance 1, 2 is a subset of the set 1, 2, 3, because every element in the first set, 1, 2, is also in 1, 2, 3, but 3 is not in the other. All right, natural numbers. There are a lot of elements in this set. Natural numbers start at 1, have 2, 3, and then this pattern goes on forever. So we use something called an ellipse, or ellipsis I should say, and it's those 3 dots that says it goes 1, 2, 3 all the way until infinity. The whole numbers are slightly bigger seemingly. So the whole numbers start at 0. That's the one thing they have that the natural numbers don't have. And they also go to infinity. The integers will appear bigger still because they don't start at any number. They go to negative infinity and they keep going and this goes to from negative infinity all the way to positive infinity. So that's the integers. All the non-fractional numbers from negative infinity to positive infinity. Rational numbers are all fractions and integers, the set we just saw. The irrational numbers, well, let me say this. Irrational numbers also have repeating decimal representation. So for example, saying for example 1/2, or actually 1/3 has the repeating decimal 0.3 with a bar over it because the 3 goes forever, but every number actually does. 5 equals 5.0 with a bar over the 0. Irrational numbers then are numbers with no repeating decimal representation. These would be numbers like the square root of numbers that aren't perfect squares, or a famous irrational number would be pi. These numbers, if you look at their decimal representation, go on forever, but they never repeat. That's an irrational number. When you put rational and irrational numbers together, you get real numbers. So again, real numbers are the rational numbers added to the irrational numbers. So in the upper right, you can see that the real numbers are the entire rectangle here. And you can break those real numbers into the rational numbers, which include the integers, whole numbers, and natural numbers, and then a separate entity, which is the irrational numbers. So let's just see if we can classify some real numbers here. In our example, classifying real numbers. To which subsets of the real numbers does each number belong? The square root of 9? Well, 3 times 3 equals 9. So that's just 3. So that'd certainly be a natural number. It'd certainly be a whole number. Certainly be an integer. And it would be a real number. But it cannot be an irrational number because it has a repeating decimal representation. So similarly, 3/10 is not a natural number because natural numbers don't include fractions, neither do whole numbers and neither do integers. Oh, one thing I forgot over on this left side is rational numbers. And that's exactly what 3/10 is. And of course, it's also real because every one of these numbers will be a real number. What about negative 0.45? Well, negative 0.45 actually has a repeating decimal at the 0, so it's rational. However, decimal numbers like fractions are not natural numbers, they're not whole numbers, and they're not integers. So again, it's rational because it is fractional or decimal, and it's real. Finally, 12 is not a perfect square. So since it's not a perfect square, we don't get an actual integer, or excuse me, a whole number back. So this can only be irrational and real, because every one of these numbers is a real number. Now notice when you're classifying, you're looking at all of the possible subsets. So a number like 3, which is the square root of 9, has a whole bunch of different subsets of the real numbers, including the real numbers itself. So that's 5 different things we would have to classify it into: rational, natural, whole, integer, and real numbers. If we're asked to compare the inequalities, that compares the square root of 129, which is not a perfect square, 121 is a perfect square, and 11.52, it'd be useful to use a calculator here to approximate. So that's what we'll do. So using technology, we see that the square root of 129, rounding to 2 decimal places, is approximately 11.36. 11.36 is less than 11.52. So there would be the inequality we would use to compare the two. That's exactly what inequalities do. They compare. Remember, we point to the smaller number. Graphing and ordering real numbers is our next example, example 5. If we want to graph these numbers, first we need to order them, just like we did before, so we're actually going to compare. So first thing I know is that negative numbers are smaller than positive, so I'll take a look at negative 2.9 and negative 7/2. Notice that negative 7 over 2 will go into 7 3.5 times. So I have negative 3.5. The bigger the negative number, the smaller it is. So I know negative 3.5 is less than negative 2.1. Next, we want to compare the positive numbers. So we look at positive 3.5, the square root of 9, and the square root of 5. The square root of 9 is 3. And the square root of 5 is approximately 2.2. And of course we have 3.5. So now ordering these, well, we'll just put these here, negative 3.5, negative 2.1. The next smaller number is positive 2.2, then it's 3, and then it's 3.5. So that's ordering them. Once I've ordered them, I'm ready to put them on a number line. And so I'm going to go from negative 3.5. Make sure you fill in that spot. Next will be negative 2.1. Positive 2.2. Number that's in between positives and negatives is a number called 0. So we're not going to fill that in because we're technically not graphing it. We're just using that to help show where places are. Positive 3 and positive 3.5. I always like to put an X. The horizontal axis tends to be called X. And there we are. So the first step is we order them. Then the second step is we graph.